Welcome back to NextEd, your go-to series from Nexaspaces Tech Education. In today's session, we'll unravel a crucial yet often overlooked concept in embedded systems: signal conditioning. Whether you're dealing with temperature sensors, pressure transducers, or analog microphones, signal conditioning is the silent hero ensuring that your data is accurate, safe, and ready for processing. Signal conditioning refers to manipulating an analog signal to make it suitable for digitization or further processing. It prepares real-world signals, which are often noisy, weak, or in incompatible formats, so that microcontrollers and ADCs can interpret them correctly. Think of it as a translator between the physical world and the digital world. Imagine you're using an LM35 temperature sensor, and the output is in millivolts. Feeding that directly into a 10-bit ADC with a 3.3V reference would give you very poor resolution. You need amplification. Or suppose you're measuring a signal in a factory filled with electrical noise. That signal must be filtered to remove unwanted frequencies. Or let's say you have a sensor outputting plus or minus 5V, but your microcontroller only accepts 0 to 3.3V. That's where level shifting and clipping come in. Let's break down the most commonly used signal conditioning techniques in embedded systems. 1. Amplification. Boost small sensor signals using op-amps or instrumentation amplifiers. 2. Filtering. Low-pass filters remove high-frequency noise, high-pass filters eliminate DC drift. 3. Isolation. Optocouplers and transformers isolate sensitive parts of the circuit for safety. 4. Level shifting and clipping. Adjust voltage levels to fit within ADC limits. 5. Linearization. Applies corrections to nonlinear sensor outputs using software or analog components. Let's look at a practical example. You have an LM35 sensor that outputs 10 mV/°C. You want to measure temperature with higher resolution and filter out 50 Hz noise. Here's what the signal conditioning circuit could look like. Use an op-amp in non-inverting mode for gain equals 10. Add a low-pass RC filter with a cutoff at 10 Hz. Connect the output to a 10-bit ADC on an Arduino or STM32. This setup ensures you're feeding a strong, clean signal into your microcontroller. Rather than building circuits from scratch, you can also use ready-made signal conditioning ICs. Some popular choices include INA333 or AD620, instrumentation amplifiers. MAX 4051, analog multiplexer. ISO124, isolation amplifier. LT1167, low-noise precision amplifier. These ICs are widely used in medical devices, industrial controls, and precision data acquisition systems. Once the signal is conditioned, it's passed to the ADC, analog to digital converter, built into most modern microcontrollers. Here's what you should remember when interfacing a conditioned signal with an ADC. The signal should be within the ADC voltage range. Avoid floating inputs, use pull-down resistors if needed. Choose the right ADC resolution based on your application. Signal conditioning is everywhere, from weather stations measuring temperature and humidity, to ECG machines capturing electrical heart activity. In automotive systems, it helps read signals from wheel speed sensors, accelerometers, and pressure sensors accurately. To sum it up, signal conditioning is not just a side topic, it's a foundational concept in any reliable embedded system. Don't forget to like, share, and subscribe to NextEd from Nexaspaces for more deep dive tech content. Drop your questions or project ideas in the comments below, we'd love to feature them in upcoming videos.